On Christmas Eve of 2024, a spacecraft no bigger than a family car flew into the atmosphere of the Sun and vanished. For 2 days, NASA's Parker Solar Probe was out of contact, 3.8 million miles above the solar surface, moving at 430,000 miles per hour, alone. Just before midnight on December 26th, a single tone reached Earth. It had survived. What it recorded inside the corona overturned an answer physicists waited 80 years for, and caught the Sun doing something no one had ever seen. This is the story of the day we made contact with a star and what it gave back. On the morning of December 24th, 2024, while most of the world was wrapping presents and boarding flights home, a machine the size of a small car fell toward the Sun at 430,000 miles per hour. At that speed, you would cross from New York to Los Angeles in about 20 seconds. Nothing built by human hands had ever moved that fast. Nothing built by human hands had ever been where it was going. The machine was NASA's Parker Solar Probe, and at 6:53 a.m. Eastern Time, it passed just 3.8 million miles above the surface of the Sun, inside the Sun's own atmosphere. For scale, Mercury, the closest planet, never comes within 29 million miles. This spacecraft flew more than 7 times closer than Mercury ever gets. And here is the part that mattered most to the people who built it. As it made that pass, it was completely alone. No signal could reach it. No signal could leave it. For roughly 2 days, the fastest object in human history flew through the atmosphere of a star in total silence. And the team that had spent decades building it could do nothing but wait. We used to say this mission was impossible. Not difficult. Impossible. And the story of why we said that, and what the spacecraft found when it proved us wrong, begins with a temperature reading that has haunted physics for more than 80 years. Most people assume the Sun is dangerous because it is hot, and they are not wrong. The visible surface burns at around 10,000 degrees Fahrenheit, roughly twice the temperature of lava, hot enough to vaporize almost any material we can make. But the surface is not the strange part. The strange part is what sits above it. The corona is the Sun's outer atmosphere, an envelope of thin, glowing plasma that stretches millions of miles into space. You have seen it if you have ever seen a total solar eclipse, the ghostly white crown that appears around the blacked-out disk. And the corona does something that should not be possible. It is hotter than the surface below it, not slightly hotter. The corona runs between 1 million and 3 million degrees Fahrenheit, up to 300 times hotter than the surface it hangs above. Think about what that means. Walk away from a campfire and the air gets cooler with every step. That is how heat works, everywhere, for everything. Except, apparently, at the one star we depend on for our existence, where stepping away from the fire makes the temperature climb by a factor of 300. Scientists have known about this since the late 1930s, when the physicists Walter Grotrian and Bengt Edlen showed that strange lines of light in the corona's spectrum came from iron atoms stripped of a dozen electrons or more, something only million-degree heat can do. They called it the coronal heating problem, and for more than 80 years it stood as one of the great unsolved mysteries in astrophysics. It is not an academic puzzle. That impossibly hot corona is the birthplace of the solar wind, a stream of charged particles that pours off the Sun in every direction and slams into Earth's magnetic field at more than 1 million miles per hour. When the Sun erupts, that stream becomes a flood, and the flood can disable satellites, scramble GPS, black out radio, and overload power grids. The corona is where the weather that touches every piece of modern infrastructure is made. For 80 years we studied it from 93 million miles away. One man decided that was not close enough. and when he first described how the sun actually behaves, the scientific establishment told him he was a fool. In 1958, a young astrophysicist at the University of Chicago, named Eugene Parker, wrote a paper making a claim that sounded absurd: that the sun is not a quiet, steady lamp, but a body that constantly exhales, throwing a supersonic stream of charged particles outward through the entire solar system, every second, forever. He called it the solar wind. He submitted the paper to the Astrophysical Journal, and both peer reviewers rejected it. One of them wrote, in effect, that Parker should go to the library and read up on the subject before trying to write about it. Parker did not withdraw. He appealed to the journal's editor, Subramanian Chandrasekhar, a physicist who would later win the Nobel Prize, and pointed out that the reviewers had not found a single error. They simply did not like the conclusion. Chandrasekhar read the paper, found no mistake, and overruled them both. The paper was published in November of 1958. 4 years later, NASA's Mariner 2 spacecraft flew toward Venus and measured the solar wind directly, blowing exactly as Parker had described. The heresy was simply true. The sun really is exhaling into space, and we live inside its breath. 60 years after that rejected paper, NASA prepared to launch a spacecraft into the source of that wind, into the corona itself. And the agency did something it had never done in its history. It named the mission after a living person. Eugene Parker was 91 years old when he stood in Florida on August 12, 2018, and watched his namesake climb into the sky on a pillar of fire. He died in 2022 at 94, knowing the machine carrying his name was rewriting the field he had founded. They named it after him for a reason. Because the question the probe was built to answer is the question Parker's whole life pointed at. What is the sun actually doing up there? Answering it required building something no engineer had ever been asked to build: a ship that could survive contact with a star. Here is the problem that kept aerospace engineers awake for half a century. The materials that make up a spacecraft, aluminum, titanium, steel, all melt or fail at temperatures the sun's neighborhood treats as ordinary. How do you fly scientific instruments into a place that unmakes the things instruments are made of? The answer, built at the Johns Hopkins Applied Physics Laboratory in Maryland, is a shield 8 feet across and about 4.5 inches thick. 2 skins of carbon-carbon composite, the same family of material used on the noses of hypersonic vehicles, sandwiching a core of carbon foam that is roughly 97% empty space. It is one of the most effective thermal barriers ever flown, finished with a white ceramic coating that throws most of the sun's light straight back at it. During a close pass, the front face of that shield reaches about 2,500 degrees Fahrenheit, hot enough to melt steel. 4.5 inches behind it, the instruments sit at about 85 degrees, the temperature of a pleasant summer afternoon. The distance between annihilation and room temperature on this spacecraft is the width of a human hand. But there is a puzzle here, and it is the question everyone asks when they first hear about this mission. The corona is 1,000,000 degrees or more. The shield is rated for 2,500. Why does the spacecraft not simply vaporize? Because temperature and heat are not the same thing. Temperature measures how fast individual particles are moving. Heat is how much energy those particles actually deliver when they hit you. And the corona, for all its ferocity, is nearly a vacuum, a handful of particles per cubic centimetre. Each one carries enormous energy, but there are so few of them that the total energy reaching the shield stays manageable. NASA's own engineers use a kitchen analogy. You can hold your hand inside a hot oven far longer then you can hold it in a pot of boiling water, because thin air hands over far less energy than dense water. The probe is not swimming through a 1,000,000-degree bath. It is threading a 1,000,000-degree near emptiness behind a shield built to shrug off the part that does arrive. There was one more problem, though, and no shield could solve it. You cannot simply aim at the sun and fly there. This is the counterintuitive part of the whole mission. The hardest place to reach in the solar system is not Pluto. It is the Sun. Earth is moving sideways around the Sun at about 67,000 miles per hour, and every spacecraft we launch inherits that sideways motion. Fire a probe at the Sun and it will not fall in. It will keep orbiting, like a ball swung on a string. To fall inward, you have to shed that sideways speed, and shedding it takes more energy than escaping the solar system entirely. So Parker Solar Probe took the long way down. Over 6 years, it flew past Venus 7 times, using the planet's gravity as a brake, each flyby bleeding away orbital speed, each orbit pulling the low point closer to the Sun, like a line being slowly reeled in. And on every pass, the spacecraft was already making discoveries. In 2019, its first results, published in the journal Nature by teams led by Stuart Bale of the University of California, Berkeley, and Justin Casper of the University of Michigan, revealed that the young solar wind is nothing like the smooth stream our models imagined. It is violent and kinked, full of hairpin reversals in the magnetic field, structures the scientists nicknamed switchbacks, whipping past the spacecraft in far greater numbers than anyone predicted. Remember that word. Switchbacks are going to matter later in this story. On April 28, 2021, the probe crossed a boundary called the Alph-Wien surface, the invisible line below which the Sun's magnetic field, not the wind, controls the plasma. Below that line, you are no longer flying near the Sun. By any physical definition, you are inside its atmosphere. NASA announced it plainly. For the first time in history, a spacecraft had touched the Sun, but the mission was designed to go deeper still. The 7th and final Venus flyby came on November 6, 2024, and it bent the probe's path toward the closest approach any machine had ever attempted. After that, there was nothing left on the calendar but Christmas Eve. On the morning of December 24, 2024, the mission operations team at the Johns Hopkins Applied Physics Laboratory was not home for the holiday. They were watching a spacecraft they could no longer talk to. This is the reality of flying inside a star's atmosphere. So close to the Sun, the radio environment is hopeless. The spacecraft cannot hear commands and cannot make itself heard. The team knew the blackout was coming. They had planned for it for years. The probe would fly the entire encounter on its own, holding its shield toward the Sun with automated sensors, making thousands of small decisions per second, with no human able to help. A pointing error of a few degrees would expose the spacecraft's body to the full furnace, and the mission would simply end, silently, invisibly, with no final signal. At 6:53 a.m., Eastern by the mission's own clock, the probe reached its record, 3.8 million miles above the surface, 430,000 miles per hour, alone inside the corona of a star at the peak of its 11-year activity cycle. And then, nothing. Christmas Eve passed. Christmas Day passed. The team waited for a single tone, the simplest signal the spacecraft can send, meaning only, "I am here. I am alive." Just before midnight on December 26th, the tone came. The spacecraft had flown through the atmosphere of the Sun and come out healthy, on course, and full of data. When the full science downlink began arriving in January, researchers had something no human being had ever possessed: a detailed record of the Sun's corona taken from inside it. Not a telescope's view from 93 million miles. The real thing up close. We assumed we knew, at least roughly, what that data would show. The Sun had other plans, and the first surprise was hiding in the wind itself. In July of 2025, NASA released the closest images of the Sun ever taken, captured during the Christmas Eve pass by the probe's onboard camera, an instrument called WISPR, the Wide Field Imager for Solar Probe, built by the United States Naval Research Laboratory. For the first time, we could watch the solar wind being born, streams of charged plasma pulling away from the corona, organizing, accelerating outward into the patterns that eventually wash over Earth. One scientist compared it to spending your whole life studying a river hundreds of miles downstream, and then finally standing at the spring where it comes out of the ground. Nikki Fox, NASA's head of science and the mission's former project scientist, put it in one sentence: "We are now witnessing where space weather threats to Earth begin, with our eyes, not just with models." And up close, the wind turned out to have two personalities. Scientists had suspected for decades that the slow solar wind came in two distinct types. Parker confirmed it. One type carries those switchback kinks in its magnetic field and appears to rise from coronal holes, the darker, cooler gaps in the Sun's atmosphere. The other is smoother and seems to peel away from the tips of helmet streamers, the enormous glowing loops that arch over the Sun's active regions. Two different winds, born in two different places, hitting Earth in two different ways. The camera also caught something with direct consequences for us: solar eruptions colliding. WISPR filmed coronal mass ejections, those billion-ton explosions of magnetized plasma, piling into one another as they left the Sun, merging like waves in a storm swell. Angelos Vourlidas, the instrument's lead scientist, described the ejections as stacking up on top of each other. That matters because merged eruptions are stronger, stranger, and harder to forecast than the sum of their parts. Every one of those findings sharpened the picture, but the two biggest results from inside the corona were still coming, and one of them took away the answer we thought we already had. Remember the coronal heating problem, the 80-year-old question of why the Sun's atmosphere is hundreds of times hotter than its surface. And remember the switchbacks, those magnetic hairpins saturating the young solar wind. For several years, they looked like the answer. Each switchback carries energy. There are unimaginable numbers of them. Surely, many scientists argued, they were the mechanism carrying heat into the corona. Then Parker flew inside the corona itself, below the Alphen surface, and looked. The switchbacks were not there. Analysis of the probe's passes through the corona, led by researchers at the University of Michigan, found that the wind just above the Sun's surface is far smoother than the wind farther out. The hairpins that fill the solar wind seem to form after the wind leaves the corona, which means the simplest version of the switchback theory cannot be what heats it. 80 years of mystery, one candidate answer, and the Sun took it off the table. What remains is a narrowed field, energy hammered upward by magnetic reconnection, field lines snapping and reconnecting near the surface, and by turbulent magnetic waves shaking the plasma. The leading view now is that the corona is heated by a combination of the two, and Parker is the only machine in existence gathering the data that can settle it. Scientists believe the answer is finally within reach. Nobody can yet say we have it. Be clear about what that means. We flew into the Sun expecting to confirm our best idea, and instead we disproved it. That is not failure. That is the point of going. And it set the stage for the strangest thing the probe has seen: the discovery that the Sun does not just throw its storms at us. Sometimes it takes them back. On December 11th, 2025, almost exactly 1 year after the Christmas Eve dive, a study led by Angelos Vourlidas was published in the astrophysical journal Letters, built from images taken during that record pass. It documented something NASA is calling the solar wind U-turn. During the flyby, Whisper watched a coronal mass ejection erupt from the Sun, and in its wake the camera caught enormous elongated blobs of magnetized solar material doing something material from an explosion is not supposed to do. Falling back in. Not all of the eruption escaped. Some of it, blobs the size of planets, was seized by the Sun's magnetic field and dragged back down toward the surface. Scientists call these inflows, and they had suspected them from distant, blurry observations for about 20 years. No one had ever been close enough to measure one. Parker measured their speed and their size for the first time in history. Here is why that should stop you. When those failed eruptions rain back onto the Sun, they do not just disappear. They physically rearrange the corona's magnetic architecture, and that rearranged architecture helps set the path and the power of the next eruption. The leading interpretation is a feedback loop hiding inside our star, each storm partially reloading the chamber for the storm after it. Our forecasting models, the ones we use to protect satellites and power grids, do not fully account for any of this, because until now we had never seen it. The Sun is not a simple engine that fires outward. It swallows parts of its own explosions and is changed by them. That is what we found when we finally made contact. And it leads to the question that makes this more than a science story. What does it mean for us? In 1859, a solar storm now called the Carrington Event struck Earth and set telegraph offices sparking on 2 continents. The sky glowed red as far south as the tropics. It was a curiosity then, because civilization did not yet run on electricity. It does now. Studies of a modern Carrington-class storm project damaged grid transformers, cascading blackouts across continents, and recovery measured in months or longer, at a cost that would dwarf almost any natural disaster in history. And today, our realistic warning time for the most dangerous property of an incoming storm, the orientation of its magnetic field, is often tens of minutes to a few hours, measured at a watchdog spacecraft stationed about 1 million miles upstream of Earth. Tens of minutes for continental infrastructure. This is what the Parker mission is actually for. Watching the wind at its source, watching eruptions merge, watching failed eruptions fall back and reload the corona. That is the raw material for forecasting models that could one day give us days of warning instead of minutes. Scientists are careful to label that a goal, not an achievement, but you cannot forecast a system you have never seen. And for all of human history, until Christmas Eve of 2024, we had never truly seen it. The probe, for its part, is not finished. It has now completed 28 close passes, matching its record distance again as recently as June 8, 2026. And its handlers report it remains in excellent health, flying through the most active Sun in 2 decades. Every few months, it dives back in. So step back one last time and look at what actually happened here. And for thousands of years, every culture that looked up treated the Sun as the one thing permanently beyond human reach. A god, a wheel of fire, a warning. In 1958, a man said it was breathing and was told he was a fool. In 2018, at 91, that same man watched a machine bearing his name leave Earth to prove it. And on Christmas Eve of 2024, that machine flew into the atmosphere of our star, went silent for 2 days, and came back carrying pictures of the wind being born. The Sun it found is not the Sun we thought we knew. Its atmosphere burns 300 times hotter than its surface, for reasons we are still decoding after 80 years. Its wind blows in 2 personalities from 2 different homes. Its eruptions collide, merge, and sometimes fall back in, quietly loading the next storm while we watch from 93 million miles away, with minutes of warning and a civilization built on wires. I keep coming back to the 2 days of silence, a small human-built machine, alone inside a star, faithfully doing its work with no one to hear it. We did not just touch the Sun, We learned that the star we orbit is stranger, more tangled, and more alive than the one in our textbooks, and we are only beginning to read what it wrote for us. The machine is still out there. In a few months, it will dive back in. Thanks for watching, and I'll see you in the next one.